Why the semi-infinity requirement? Because if the media are finite, there would be multiple reflections and transmission, and the waves will be more complicated than the three components mentioned. In fact, this problem is the least useful, but also simplest in the topic of planar medium optics, and serves as an introduction to the basic concepts of planar interface phenomena, from thin films to planar waveguides that will follow later. All real-life applications involve the plane wave approximation of a light beam. Light beam presentation here makes the interference region between the incident and reflected waves distinct from the wave component themselves. It also serves to elucidate the concept involving the cosine irradiance law for practical matters on beam intensity and power, as will be shown in examples. Intuitively, we tilt a cell phone display to a small incident angle with respect to the eye, to avoid strong ambient reflections. This is a common sense example of the effect of incident angle on reflection and transmission. We generally have the ability to distinguish transparent dielectric media with different refractive indices. Diamond sapphire, for examples, appear optically denser than glass and water, and we can tell stronger refractive effects. If a transparent solid object is dropped in a transparent liquid with the same refractive index, the object would magically disappears because there is no reflection for us to tell the physical boundary and the existence of the object. Since most transmission and reflection phenomena is a matter of the relative difference between the two medium refractive indices, the incident medium refractive index is also a relevant parameter, particularly for the total internal reflection effect. The use of a finite beam is also relevant to illustrate the Gauss-Hanschen shift. Besides vectorial and regional graphics to represent the light beams, wave illustration is essential. The app has two types of graphics: density plot, as shown here with color coding to represent the field amplitude. The other is 3D plot. In 3D plots, the height, that is the vertical axis, represents the scalar amplitude of a field component. It can show more clearly a field continuity across the interface. And likewise, the discontinuity of the electric field normal component in the case of TM polarization. The vector basis of polarization is important because it helps greatly to simplify the problem. For the two basis components shown here, all the waves, reflection, and transmission have the same polarization. This simplicity is not true for, say, arbitrary elliptical or circular polarization bases. Mathematically, it reduces E and H field vectors to just a single scalar component with simple equations. All the earlier illustrations are for TE polarization. Shown here is TM polarization, which is mathematically the same as TE, with the transverse H field is in lieu of the E field. The incident light wave can have any arbitrary polarization in its plane, perpendicular to its K vector, shown as the rectangle between the E and H vectors. All three waves have different plane orientations. There is only one axis common to all three, and that is the transverse, labeled as y-axis here. This is the reason why the problem can be conveniently set up for either TE or TM. Once this component is known, Maxwell's equations can be used to derive the other components for each wave. If the incident wave has a general elliptical polarization, it can be decomposed into two components. One is along the transverse axis, for example, u basis vector shown here, and the other, v, is perpendicular to it. Each component, Te or Tm, is solved separately, and added together afterward. Measuring the change of polarization to determine a planar dielectric structure, such as thin films, is the basis of a very important measurement method known as ellipsometry. Later, we will see example applications such as using the total internal reflection phase shift in the Fresnel ROM to change a beam polarization. The waves are calculated simply by using the most general solutions of Maxwell's equations in each medium that match the initial condition. For the incident wave, it is straightforward with known k-vector and frequency. For the reflected wave, it a general wave of the same frequency, but can have arbitrary k-vector, and even other polarization components. However, it can be shown that given the transverse incident polarization, other non-transverse reflected polarizations cannot exist. Given the continuous translational symmetry with respect to z and y, the reflected wave has the same beta k component along z-axis, and must have an opposite sign k1, otherwise it would be the same as the incident wave. Hence, the reflected wave must have an equal but opposite angle with respect to the incident angle, and its wave solution is completely known except for the amplitude. For the transmitted wave, it a general wave of any frequency and k-vector, except that its polarization must also be the same as that of waves in medium 1, otherwise, the boundary condition would not be satisfied. More about the boundary condition later. Separation of the three wave components is only a mathematical structure, not a physical reality. All the waves in a given medium add together as a single physical entity, as it will be seen next. Even separating the waves of the two media is a mathematical abstraction. The physical reality has only one wave solution throughout the entire space and time. It means that the two waves in the two media are not independent, but must satisfy the same physical laws at their interface boundary. In terms of the mathematical model, the wave expression of each side must obey the physical laws at the interface, which is the plane of x equal to 0 in this case. This is a video that shows two basic laws of electromagnetic phenomena. On the left-hand side, it shows how a current or electric field flux can generate a magnetic field. On the right-hand side, it shows how the magnetic induction flux can in turns generate an electric field and affect a current. Both laws can be applied to a light wave at an interface. On the left-hand side, there is no current, but there is an electric flux, which can induce a magnetic curl as represented by the integration of H field around a loop. Similarly, on the right-hand side, there is a magnetic flux inducing a curl of electric field. As the loop of either case is shrunk, the enclosed area vanishes, leading to the implication that the tangential component of the curl field must be continuous across the interface. Consider the interface of the two dielectric media. The two sides must match for continuity with respect to time and space, and also amplitude, which will be considered later. The transmission wave is plotted for different frequencies. It is clear that its frequency must be exactly the same as that of the incident wave, otherwise, the two sides could not be matched at all time. Given its frequency being fixed, the transmission wave must have a definitive magnitude of its k-vector. It can point in any direction. However, there is only one direction for which its wave at the interface matches with the incident medium wave in both space and time, which is when its beta, the k component along the z-axis, is the same as the beta of the wave in the incident medium. This leads to a definitive relationship between the transmission angle versus the incident angle theta, and the refractive indices of the two media. This is also known as Snell's law or Descartes' law, depending on which side of the channel. The previous application of the tangential continuity requirement focuses only on the interface wave space and time behavior. It is necessary that the field amplitude must also be matched. It is actually trivial to match the amplitude, once the functional forms of space and time are matched, as they can be dropped from both sides of the equation, leaving only the field scalar amplitude terms. However, there are infinite number of solutions for the two amplitude terms, T for transmission, and R for reflection with this equation. The reason for infinite T and R solutions above is simply that not all the tangential continuity conditions are already applied. It was applied only to the transverse field, either electric or magnetic. There is another tangential component, which is that of the other field that is in the incident plane. Here, the transverse field is electric, hence the other field is magnetic, shown as the blue vectors. Together, the two fields define the phase front plane of each wave, represented by the rectangle spanned between the two vectors. It is the tangential components of the H fields that must be considered for the continuity requirement. The graphic illustration shows the magnetic tangential components as vectors that are projected from the H fields, which are blue, onto the interface, lying along the z-axis. The components in the incident medium are shown as magenta color vectors, and that of the transmission medium as the yellow vector. The magnetic field tangential components can be easily obtained by applying a Maxwell's equation to the known transverse E field. In medium 1, after some straightforward algebra, it is just 1 minus r multiplied with a factor. The minus sign here, as opposed to the plus sign for the transverse E field above, is significant in that the k1 component of the reflection wave is opposite to that of the incident. On the vectorial graphics, applying the right-hand rule of E cross H equal to k, shows that the relative alignment of H tangentials of the incident and reflection waves cannot be the same as that of E fields, and vice versa. For the transmission wave, the result is straightforward. It is just T, multiplied by a factor. Together, applying the continuity condition leads to a simple linear equation. With two tangential continuity equations, one for E field and one for H field, coefficients R and T are uniquely determined, giving a unique wave solution for the entire structure. Three-dimensional plot can illustrate the field continuity. The left-hand side shows E field, the right-hand side shows H field. To summarize, the solution for the transverse electric polarization case is quite simple. Since for most dielectric materials, the magnetic permeability μ is practically 1 in the optical frequency range, one can neglect all the μ coefficients in the formula. The mathematical symmetry between the transverse electric and transverse magnetic formulation is quite clear in the results. For the case of transverse magnetic, the formulas are practically the same, but with epsilon substituted for μ's. However, in real life, the practical difference between the two polarizations is quite significant, since while μ coefficients are practically 1, the same for most dielectrics, the dielectric constant epsilons are not, which is exactly why the refractive index is an important optical property. The 0 Tm polarization reflection at Brewster's angle is a typical example of Te and Tm difference. A close observation shows that the formulation leading to the R and T coefficients for transverse magnetic is different from the two simple equations of the Te case. In fact, it is done differently, based on an approach known as the transfer matrix method that is mathematically more elegant and practical for applications. The reasons will be discussed next. The single planar interface structure between two dielectrics is a most elementary component of a class of structures consisting of many planar dielectric layers for various important applications. Shown here is just a conceptual illustration. The number of layers can be in the hundreds. There are two configurations of light propagation for applications with these structure. For thin film filters, dielectric mirrors, or optical resonators, including passive filters or vertical cavity surface emitting lasers, the structures are designed to engineer light behavior for propagation through the layers with any incident angle, similarly to the configuration studied here. It can be as simple as a single or few layer for anti-reflection coatings on common eyeglasses. Or it can be complex multiple coupled cavity structures for narrowband, flat top, low ripple filters for optical communications. The other configuration is for light to propagate parallelly in the planes of the layers, known as planar waveguides. All edge-emitting diode lasers are applications of this configuration. It is not enough to confine light in just one dimension, which is the direction normal to the layer planes, and which is the x dimension in this example. It is necessary to confine light also in the y dimension, and to allow light propagating only along the z dimension as a light wire to conduct photons in a photonic circuit. This configuration is considered as two-dimensional planar, and the mathematics can still be applied as a reasonable approximation. For a structure with many layers, it is not practical to apply the boundary condition manually one by one as shown above. By exploiting the linear property of the problem, the transfer matrix approach simply reduces each layer, known as a segment, to a matrix that operates on the field values of one side to yield the values of the other side. In other words, the matrix, quote-unquote, transfers the wave solution from one boundary to the other. At each interface, there is an interface matrix to apply the appropriate boundary condition, either Te or Tm, between two segments. The entire problem is represented as multiple linear operations, that is, matrix multiplications for an entire structure. This will be discussed in part 3 of the lecture, and will be essential for all the topics that follow.